Well, we'll start in just about a half a minute. Welcome back, everyone, so far. Hello. Well, looks like we can start. Welcome back, everyone. Appreciate people making it in right before Halloween. Usually, this is not the easiest class to attend, so welcome back. We'll finish off week 10 working in null spaces. And if we have a little bit of time, we'll start section 4.3, but it's mainly here as a just in case. 4.3 is kind of a nice section because we're, in a real sense, just revisiting old material, linear independence and linear dependence. We have a wider view of what a vector space is, and so we're just going to look in the definition again, see what might be different if we're dealing with polynomials and other functions, but it's another kind of refresher on that kind of material. And 4.2 really isn't too bad either. 4.2 is going to be kind of preparation before we get to chapter 5, eigenvalues, eigenvectors. And it was a section that we could have done in, say, section right after 1.4 or 1.5. It fits in with chapter 1 material pretty nicely. The other big announcement is on Friday, before doing really anything at all, first thing I want to get settled is on the Canvas page. I'll be including the information here for the exam material, the coverage on the exam, the review problems, just like before. So I'll try to get that squared away right away. If you're the kind of person that likes to study early, you'll have that material ready to go. So that's our plan so far today. I didn't have any special Halloween problems or anything like that prepared, unfortunately. Usually if Halloween falls on an ordinary class day, I usually just cancel it since that's a big distraction. But we already had a fire alarm that caused big problems earlier in the semester. So to just stay on track, we'll just do some more math. That's scary enough, I guess. But any questions at all, folks, before we jump back in? Okay, well, here's where we left off. We're looking into the null space of A. To state it as a set, it's pretty simplistic. It's a set of all vectors that satisfy the homogeneous equation, A times X equals a zero vector. So here's its full definition. You could be more specific and say, where did the vector X actually come from? If A is an m by n matrix, then X has to come from the vector space Rn. So the number of columns has to be the number of entries in X, and that's just so that the matrix equation A times X is actually defined. So the null space sends all the vectors into the zero vector, or is this collection of all vectors X that gets sent into the zero vector by that transformation, A times X. Or we could state it as a mapping, and it'd be the same concept. So we looked into very briefly at the end on Tuesday's class. If you have a particular matrix A at a particular vector X, you can determine really rapidly if just that one vector is in the null space. You don't actually have to crank out the null space. Just take A times X. We did that and got something that was non-zero. So our automatic conclusion was X is not in the null space of A. If we had gotten 0, 0 here, we'd have said, yes, it is in the null space. But part B is a totally different kind of question. It's now asking, well, what is the null space? X is not inside of it, so what is in it? It could be just one vector. We know for sure the zero vector is inside there because the zero vector satisfies that equation by default. That was what we referred to as the trivial solution way back in section 1.5. So we want to know, is there more than just the trivial solution inside the null space? But that means we're just doing a very familiar problem. We're going to solve A times X equals 0, I shouldn't have scrolled just yet, and write out the solution set in parametric vector form. So here's the matrix A. We need to solve A times X set equal to the 0 vector. And again, it's a pretty friendly problem. We can go immediately to the augmented matrix. This has augmented matrix. Take the original matrix A we have up here. 1, 0, 2, 1, going column wise, 3, -4, 0, 1, 0, 5. Now it's augmented with the 0 vector. And row reduction on this goes pretty rapidly. It's in echelon form already with that 0 placed there. We need to eliminate the 2 right where the red dot is to get it in row reduced echelon form. So copy row 2, 0, 1, -4, 1, 5. We'll take -2 times row 2, add it to row 1, and that gives us 1, 0, positive 8 plus 3 for 11, -2 plus 0 for -2, and likewise a -10. 0 on the right column can't change due to it being just 0, 0. And now it's in row reduced echelon form. We're just about done with the row reduction. Here's where it becomes a pretty good review problem. These are tricky questions in a certain sense because a lot of it is just kind of organization. The vector x's that we're looking into have 5 different entries. So we have to say precisely what is this going to look like as a span or the parametric vector form. So list out x1, x2, x3, x4, x5. You don't necessarily have to, but it's here just as a quick reference. Then just rewrite the actual system of equations that we get when we transfer from the matrix to those equations, but solve for the first variable x1, the first basic variable. This gives us x1 equals -11x3, positive 2x4, plus 10x5. Next basic variable is x2, since it corresponds to a pivot. So solve for x2. In terms of the other free variables, it gives us 4x3 minus x4 minus 5x5. Then recall x has 5 different entries, and we're trying to build out the span of those certain vectors x that get mapped into the 0 vector. So we should list out 5 entries here as well, just so that we have everything in the right order, the right size of the vector. So now we're essentially just listing out the free variables. x3 is equal to 1 times x3. Likewise, x4 equals 1 times x4. Don't really have to put the ones there, but that's just to emphasize this is the scalar we're going to import into our vectors. And then finally, the last free variable is that x5 equals 1 times x5. With doing all this preparation, we're ready to say what the actual null space is. It's the span of a particular set of vectors. And we have a times x set to the 0 vector implies x, which is fundamentally a vector of this size, x1, x2, x3, x4, x5. This is what all those entries are going to look like. But we can rewrite this in a nice compact way by saying, take this x3, this is now as a parameter for the so-called parametric vector form. All the scalars that correspond to x3 go -1, 4, 1, 0, 0. Then do the same for the next parameter, x4. Column vector is 2, -1, 0, 1, 0. Last one is plus x5, and let me see if I can reformat this slightly differently. I didn't quite put in enough space here. x5 equals 1 times x5. Let me delete that line below. Okay, it's good to kind of organize this because a lot's going on. We don't want all these results jumbling together at the lines above. So finally, for the x5 scalar, the constant vector is going to be 10, -5, 0, 0, 1. And we can say, just to be a little bit more descriptive, this is how you can describe any solution for ax equals 0. That means this is the full description for x, where x is described in this way. X is in null A if it satisfies a times x equals 0. The only thing you have to change is pick a values for x3, x4, and x5. So we can say such that x3, x4, x5 are in R. So just about there. We want to rewrite the null space as a span of a set of vectors. But any questions at all, folks, getting to just this point here? Okay, with what we're looking at so far, this is essentially just the definition for the span of a set of vectors. We take a look at how this is defined from section 4.1 or all the way back in chapter 1. The span of a set of vectors is just a scalar multiplying a vector plus a new scalar multiplying another vector. It's just a big linear combination where your scalars or weights can be any real value in R. Whether you call them C1 through CP or X3, X4, X5, we're really looking at the span of a set of vectors. So we're going to write it in this form. The constant vectors are the main superstar to this show that we're going to reuse in chapter 5. So finally, we can say the null space of A is just the span of those three constant vectors, -11, 4, 1, 0, 0. When we're writing out a span, we don't put in any values such as x3 or the pluses whatsoever. We're just listing the constant vectors. 2, -1, 0, 1, 0. And the last one is 10, -5, 0, 0, 1. So that's finally the null space of A. We wrote it as the span of a set of vectors. And this whole technique from just getting to this line here, the parametric vector form, seeing it as a span, are just ideas we're going to reuse later. Well, we did, folks. If you want to know what the full null space is, this is it. If you take any one of these vectors, multiplied against the matrix A, this part right here, you'll get the zero vector guaranteed. And take any linear combination of these three vectors, and you'll get the same result. It tells us this vector that was provided is not a linear combination of these whatsoever because it wasn't in the null space. Well, that's kind of a nice problem in a certain sense. It's really just a refresher of a lot of chapter 1 that we did earlier in the semester. Any questions or comments getting down to that last step? Okay, one thing that's kind of nice about writing it as a span is it reveals something about this null space. If we look into chapter 4.1 again, the major theorem of chapter 4 is this theorem 1. It tells us the moment you can write your set as a span, it's an automatic subspace. So that's the idea we have right here. We wrote this as a span, and so we can say, therefore, null A is a subspace of R5, because these are vectors with 5 different entries. The big question we want to resolve, however, is that always true? Can you always write the null space as a span of a set of vectors? Turns out it is true, but that's a hard thing to prove. That's a lot of work to show. We can prove that the null space is always a subspace of the right vector space here in a different way, a little bit easier, just by using the ordinary definition. So we'll take a look into that later on in the notes. But first, let's practice one more big concept with the null space. The null space is certainly a subspace of Rn, and we'll prove that in our next problem. But this corollary down below is just a shift in a point of view that's just as important. So corollary, just as a quick definition, is just an automatic mathematical fact that follows from a prior theorem. So if we say the null space is a subspace, then the solutions of a homogeneous system of equations and system of m equations and n variables is a subspace of Rn. These two theorems are somehow highly, highly connected. So let's take a look at first what theorem 2 is saying, the next major theorem of chapter 4. So far, all these major theorems are just the theorems that says something is a subspace. So that's kind of curious in a way. First, let's just rewrite what the null space is. Null A is a set of all vectors x in R something such that A times x equals the zero vector. The matrix A is of size m by n, so that's m rows and columns. That tells us to make this multiplication work, the vector x has to be n by 1, and it tells us x has to come out of Rn itself. So that's how this part connects. The number of columns in the matrix A is going to inform us which subspace we're dealing with. So those two parts right here are always going to match up. That part's not a coincidence. And when it says the homogeneous system of m equations and n variables, that's much like thinking about the m by n matrix right here. It's also a subspace of Rn. Just as a refresher, when we say the homogeneous system, we're going all the way back to section 1.5. A system of equations is said to be homogeneous if it can be written in the form A times x equals a zero vector. And that's the connection right there. The null space is defined as the set membership condition being a homogeneous equation. And so the corollary is just saying, if you look at this as a matrix equation or as a system of equations, you're really doing the same kind of work. It's still going to be a subspace of Rn. So it's kind of nice to see these definitions coming back. This one turned out to be a gigantic, pivotal cornerstone definition because we later on used the concept of solutions to homogeneous equations as determining whether something is linearly independent or linearly dependent. And now it connects with the null space as well. So example 2 is a tricky problem. If you're being asked if W is subspace of Rn, you could work really hard on this. You go back to the subspace definition, check out parts A, B, and C like we did in chapter 4. But if you can write it as a homogeneous system of m equations and n variables, your work is completely done. So really, this is all you have to do for a problem like this one. Just rewrite W as a column vector PQ RS such that, let's look at these equations and see if we can really write this as a homogeneous system. We could write down the matrix equation, but this is telling us you can just write down the equations themselves. So going back here, subtract 4s, and we have the equation P minus 3Q minus 4s equals 0. On the second equation here, subtract s, subtract 5r, and we get an equation 2p minus s minus 5r equals 0 as well. And notice what could have make this a problem for us. If this was p minus 3q equals 4s plus 1, it's no longer homogeneous. And then the whole corollary is off the table. It's probably not a subspace of R4 any longer. But we got this to equal 0, much like in the matrix equation, it's set equal to 0. And so this is just the solution set to a homogeneous system. Well, how many variables do we have? There's 4, P, Q, R, and S. So that's the n variables corresponding here. And that's why it makes sense that this should be for R4 as a subspace. Really a fast problem. All we have to say is, therefore, W is the set of all solutions to a homogeneous system of equations. There are 4 variables. And so it is a subspace of R4. So pretty fast problem. It's kind of like using, say, in section 4.1, this theorem 1. If you can write something as a span of a set of vectors, your work is also automatically done. You don't have to go through that entire subspace definition. Well, any questions at all, folks? Getting through example 2? Absolutely. The only difference is if you say if it's a null space, usually you want to write down the matrix A, but that's not really a requirement. It's just usually null space goes with the matrix. But if you just said W is a null space, that would have worked out just fine as well, even without saying what the matrix A is. Just kind of a different point of view. Null A is usually talking about the matrix equation, but it's not a strict requirement. And this corollary is just mentioning you're dealing with a system of equations, no longer in matrix form. Does that make sense with that question there? Yeah. Awesome. Other questions so far? Okay. So far, it looks like the null space should be a subspace of Rn, but this is on shaky ground. It worked out here because we could write the null space as a span of set of vectors, and then that's automatically just theorem 1 from section 4.1. But questions still loom. Why is this theorem 2 true? Why is the null space always a subspace of Rn? Saying that you can always write down the null space as a spanning set, it turns out that is true, but that's not easy to show like we mentioned before. We can show this directly. So just for the sake of practicing what is the subspace definition one more time, let's actually prove theorem 2 ourselves. It's not as bad as it seems. It's really just connecting two big ideas. What is the null space in the very first place? And what are the three different parts of the subspace definition? So let's give this a try next. Best way to start this one is write down exactly what the null space is. Our matrix is of size m by n, so the number of columns is going to correspond to which subspace we're talking about. It's not going to be Rm, it'll be Rn to correspond to the number of variables, which is the number of columns in the matrix A. So just to be specific, let's write null A. It's a collection of all vectors x, and let's say it's slightly more specific, all vectors x in Rn, such that A times x equals a zero vector. So all the vectors that just get wiped out when you multiply by A. Not exactly wiped out, but sent to the zero vector is more specific. So to do this, we have to look at the three big definitions of this subspace problem, or the three big parts of the subspace definition. Sorry, tripping over my words there. Part A is about the zero vector. But we have to pick this specific zero vector. If we're saying subspace of Rn, we grab that zero vector. So let's say let that be the zero vector of Rn. Well, because we sense the zero vector of Rn, we know it has of size n by 1. It's just a column vector with all entries identically 0, n entries in total. We need to show that the zero vector is inside of this null space. And there could be problems if we said this is Rm, it wouldn't work out. The matrix multiplication would be incompatible. So that's something to actually check. Can we really multiply that zero vector by that matrix A? Just depends on the size of that matrix A. So let's write this out. Then that matrix A times the zero vector. Let's check the sizes. Our matrix A is of size m by n. The zero vector is of size n by 1, and that's good. That means matrix multiplication is compatible here, and our step here is done. A matrix A times the zero vector will give you the zero vector back, provided that multiplication is defined. We just get the zero vector. And what's the size? This would be size m by 1. So major thing is we got the zero vector that came out. And this tells us, let's say here, this shows that zero vector is in null A. So one part definitely works. We were probably expecting it should contain the zero vector, because that's just the trivial solution to the homogeneous equation AX equals 0. We were told in section 1.5, back when we did this, the homogeneous equation always has the trivial solution. And that's just a way of saying the null space of A always has its zero vector. Major thing we were checking is that the right subspace? Is it Rn or Rm? Turns out it has to be Rn specifically. Well, that takes us down to parts B and C. Any questions with verifying zero vectors contained in the set? Okay, so let's set up the next two parts by grabbing the three things we would need. We have to show closure of vector addition, so we need two vectors inside the null space. Let's start by saying let U, V be in null A. And we're also going to need an arbitrary scalar. So let's say, and let C be in R. Since we're showing closure properties, we have to show somehow on paper, how do you get inside the set null A? Turns into a set theory problem. You're inside the set null A if you satisfy this set membership condition. So it's pretty much like the problems we saw in chapter 4, just a new kind of context. And because we already picked objects inside of the null space of A, we should say what it means for U and V to be in there in the very first place. Let's write here, just as an additional line to organize our thoughts. Since UV are in the null space, we have A times U is automatically the zero vector, and A times V at the same time is automatically the zero vector as well, because they have to satisfy that condition. This allows us to walk through the two parts in a pretty fast way. I accidentally scribbled there. Part B is going to say, then U plus V is in null A. We have to justify this, so let's continue by saying, because U plus V, well, what do we do with U plus V? We have to take this whole thing and put it there. So we're going to pre-multiply by the matrix A itself. A times U plus V is going to turn into, well, that's just AU plus AV. But because U and V came from the null space, with these equations we already wrote down, we know both of these just come out as a zero vector. So this turns into the zero vector plus the zero vector. We know that if you take the zero vector added to itself, we get the zero vector back. But that's all we had to show. A times something results in the zero vector, and that's what we have. So this justifies closure works for vector addition. U plus V is indeed in the null space. We satisfied the set membership condition way up here. Now just one more closure property, and we'll have that this is a bona fide null space. It's kind of wild that this is the easier proof. Trying to show that the null space A is always the span of a set of vectors takes some work. It's easier to show it works for a particular matrix A, but showing it in full generality is lots and lots of writing. This is the faster approach to prove theorem 2. Any questions or comments before we go for the last closure property? Okay, so we've showed we're closed under vector addition. Now we're going for the scalar multiplication. We've already designated a scalar C to use, so this is in scope of all parts now. So in part C, let's just use the vector U. You could use the vector V if you like. Some people would just redefine a new vector U right here, but we can say U and V is in scope of the entire rest of the argument the moment we defined it. So let's say next C times U is in null space of A. That's what we want, and we have to justify this. So let's say because we have to take C times U, that's the vector we want to throw inside the null space, then always, if it's a set, go to the set membership condition. We're just doing set theory really at this point. We get inside here, if we pre-multiply by A, and get the zero vector out. So that's how we organize what to do next with C times U. So come back down below here, take A times C times U. And there's a theorem all the way back in section 1.4 that tells us there's a sort of associativity that happens here. A scalar C, right where the red dot is, can commute to the left of A. That's kind of nice because then we can write that this is C times A times U. We already know A times U is the zero vector, so we get that this is equal to C times the zero vector, which results, if you scale the zero vector by any scalar whatsoever, you get the zero vector back. So this was the x that we threw in this definition up above here. We took A times that x, we got back the zero vector like we should have, and that tells us this was not a lie. Indeed, the scalar multiplication of C times U is inside the null set of A, since U itself came from null A. That's our last closure property. We're closed under scalar multiplication. This works for every single scalar C you could come up with because we never specified one. It was completely arbitrary down here in the justification. And that closes the whole problem. Parts A, B, and C hold, and we can say, therefore, null A is a subspace of Rn. So that's our major subspace that we're going to be looking into in this chapter and the next. But any questions at all, folks, on just looking into the subspace definition again through this problem? Okay, that subspace definition, it feels like a pretty big problem to always work through because of the three parts, the two different sets, the subspace, the overall larger vector space. So I felt like just looking at it again down here in the notes is a good problem, just to refresh ourselves on that. On the next portions that we're going to take a look into, we're just going to be getting into other subspaces. So here is the next one, the column space of a matrix A. This one's kind of cool in a way because it's a nice definition. Null space had a kind of a hard way that it was defined. It had a set membership condition we had to check. It was a homogeneous equation we were looking for the total solution set to. The column space is a little bit more straightforward in my opinion. The column space of an M by N matrix A is going to be denoted by col A. So that's going to be our way to say column space of the matrix A. And oftentimes they put a parentheses around it. It kind of reminds us of function notation. It's a type of function that accepts a matrix and spans out, or excuse me, outputs out a span. It's a set of all linear combinations of every single column of A. So AI is the ith column of A. And this is probably the cleanest way to define it. The column space of A is a span of A1, A2 through AN, where those are the columns of the matrix A. But every one of those columns has M entries because there's M rows in the matrix A. That means our next big theorem, another subspace theorem, is that the column space of an M by N matrix is a subspace of Rm. And just so we can get these dimensions about right, if A is M by N, then null A is a subspace of Rn. So those are two things to keep in mind and separate in our mind. The null space is about the number of columns. That's where the subspace is contained in. The column space is about the number of rows m, and that's where that subspace is contained in. So those are easy to kind of get backwards. So it's good to just, the moment you define column space, think of it in terms of the null space as well at the same exact time. So theorem 3 is a nice fact. It tells us we have a subspace immediately. And for example 4, we'll prove theorem 3. I put here that this is a potential question on exam 3 and even the final exam, potentially both. But it's kind of a nice question when you see it come up. Anyone see what the big idea should be for proving theorem 3? Let me throw down a hint while we're thinking about it. Here's pretty much our big idea on this one. This one is a nice proof. If you're to prove theorem 3 that the column space is a subspace of Rm, all you really have to do on paper is say what the column space is in the very first place. But the key ingredient is right here when you say it's the span of the columns of A. Because theorem 1 just jumps in immediately and says, anytime you write down the span of any set of vectors, you have a subspace. So this is kind of the nicest, cleanest proof ever. Doing the one for null space is messy. We really just had it targeted by the underlying definition. But that's one way the column spaces is kind of straightforward. If you write something down as a span, you have an automatic subspace. So let's write it down just for the sake of completion on this one. For proving theorem 3, then we start with the m by n matrix A. Let A be an m by n matrix, and let A1, A2, up to AN denote the columns of A. We can say something particular about each one of these column vectors that forms the matrix A. They're all in Rm. We can say here, then AI is in Rm. And now we're just about done. We're just making sure we have the subspace of the right vector space in the first place. We can say here, since the column space of the matrix A is the span of A1, A2 through AN, it is a subspace of Rm by theorem 1 of chapter 4. And this was pretty wordy. You might shorten it up and be a little bit more terse. I put a lot of extra words just to set the notation and also to emphasize the Rm in this problem. And that's just the direct use of theorem 1 below. The subspace V that was highlighted in blue is Rm itself. And that's why we're being particular when we're saying that they all have, or excuse me, that every column vector AI has m entries, so it came from Rm itself. That means when we span these vectors, we're spanning vectors from the vector space Rm, V, and the part where it's a subspace was just the automatic portion. Hardest thing really is just making sure you're talking about the right overall vector space, Rm itself. Well, that's kind of nice in a way. Next problems will just work with this particular new space, the column space. Any questions at the moment with getting through example 4 or the main content? Okay, example 5 is really just about working with what is the column space in the first place. We have a particular set here. This looks like this one would be a subspace of R3. And we're wondering then, if it is, could we rewrite it for the right matrix A as a column space itself? Actually, this problem is pretty fast, and the main idea is very similar. Once again, in section 4.1, where we took this column right here, decomposed it in this sort of way, and we did all that work because we want to get a span. That's the whole idea with this problem. The column space is the span of the columns of A. So if you can take something like this and write it as a span, all you say now is, those are my columns of A. And the whole problem is done at that point. So let's start off by saying we have column space of A equals, let's decompose this. We're rewriting it in parametric vector form as A times the column vector -1, 1, 3, plus B times the column vector 2, -2, -6, such that AB are in R. So all I've done is the very first step is decompose this into now parametric, A and B are the parameters, vector form. These are the two vectors. Then once we have that, we observe we're essentially just looking at a span. This is a linear combination. A and B are free to be any value whatsoever as parameters. So we can just rewrite this whole thing as a span of two column vectors. So this is nothing but span -1, 1, 3, 2, -2, -6. Then we just go back to what is the column space in the first place. The column space of A is all linear combinations of the column of A, but this is a nice clean way to say it. The column space of A is just the span of the columns of that matrix A itself. That's what we have down here to connect it with. And so we can say, we have the column space of A is a span of these columns, if and only if that matrix A itself is -1, 1, 3, 2, -2, -6. Then the whole problem is over. And you probably can see how it connects right down to here in a very, very rapid way. But taking the time to actually write this down is just seeing how the underlying technique, parametric vector form, the definition of what the column space is in the very first place, all connect together. So I would encourage you to write out like this just to make those connections. This get some familiarity with how these techniques work and definitions. But we did it, folks. These are pretty fast problems when it comes down to column spaces. Any questions or comments at the moment? Okay, well, let's take a look into the next concept. But maybe before we jump right into that next concept, looking into this column space, there's a pretty insightful comment made, I think, like week 3 or 4 of the class about theorem 4 in chapter 1, whether this connects with the concept of column space, and it absolutely does. So let's go way back to section 1.4, and here's that theorem 4. It's a statement of logically equivalent concepts A through D. It's accessed by the pivot being in every row, and have a lot of interesting statements. But in particular, one statement said, the columns of A span Rm, much like we have here, the column space of A is a subspace of Rm. And if we say the columns of A spanning, well, the column space is the span of the columns of A. We could have just totally rewritten this theorem at this point now and say column space A equals Rm itself. That's just a new way to think about this theorem. So that's going to connect with the next question. Is the column space of A equal to R3? And give a short explanation. Here's that theorem again. Well, for the column space of A to equal R3 in our problem, we would have to have a pivot position in every row in our matrix A. It looks like it's the wrong size, though. We have more rows than columns. We're only going to get 2 pivots in this particular matrix. So there cannot be a pivot in every row. That means the columns of this matrix A do not span R3. But just a different way to verbalize this, we would say the column space of A is not R3 itself. We're really saying the same thing. We're just using our new notation here for a column space because the column space of A is just the span of the columns of A, much like what part C is saying here. So it's another fast problem. We spent more time just thinking about the concepts going together. We can say here, just to finalize this one quickly, A can not have a pivot in every row. And so the column space of A, it's a subspace of R3, but that subspace is not the entire vector space R3. So we'll say here, column space of A is not R3 by theorem 4 of chapter 1. And at this point, we're done with the problem. Any questions at all, folks, thinking about column space so far? Okay, there's other concepts like, say, for example, there's a row space, the span of the rows of the matrix A, but the major ones we're going to be focusing on in this course are column space and the null space. So here's that theorem 4 just as a reminder that the invertible matrix theorem has lots of use, but theorem 4 itself is a pretty important concept. Let's see if we can squeeze it up here with the last problem. And just because we have new definitions, we could rewrite part C by saying this. Part C is this equivalent to column space A equals Rm, same exact concept. That could just be, say, a part E. We could extend theorem 4 by putting in that concept, but really it's just part C with slightly different language, just different notation thrown in. Only thing we didn't have in chapter 1 was a notion of a subspace because we had to formally define vector space first. That's why we didn't put column space there at that time. Well, last problems are just kind of connecting both thoughts together all at once. We're going to look into a particular matrix A and a column vector, determine if it's in the column space and in the null space. Example 6 is a more of a quick concept question, just to think about what subspaces do each one of these things actually belong to. So let's try out both of them just to get a feel for these last ideas. So this matrix A in example 6 is of a particular size, 4 by 2. We want to know the value of K such that the null space is Rk. What value of J do we have such that the column space is a subspace of Rj? There's a similar problem like this on the homework, and these have a way of being a concept question as well in an exam setting. I think the best way to think about this, imagine you're in an exam and you kind of got mixed up. You might know this for sure at the moment, but being a little bit stressed out in an exam has a way of allowing knowledge to just kind of disappear that you once had. Best way to be really sure about the null space is just to write it down. Null A is going to be equal to set of vectors x such that A times x equals a 0 vector. So if you just write this down, it gets you started because we know the size of A. A is in R 4 by 2. That's just another way of saying it's a 4 by 2 matrix. That means x has to be 2 by 1. And then this just, 2 by 1. There we go. That allows the matrix multiplication to be compatible, multiplying the vector. And so this implies immediately null A is a subspace of R2. In other words, K is 2. So that's the resolution to this one and how to think through it if you just got mixed up, or you want to be extra sure. Maybe you have a little bit of extra time in exam 3, or maybe in a final exam setting. This is the way you can convince yourself you've got the right dimension, R2. Same thing works for the column space, but any questions at the moment with the null space version? Okay, let's take a look at this from the column space point of view. A is a 4x2 matrix, and we know that the column space of A is the span of the columns of A So that'd be a good way to get started on this one. If you span the columns of A, the next thought you'd want to have is, well, the columns, if it's in R4x2, they would have 4 rows or 4 entries. So we can say here, each column has 4 entries, and this alone implies the column space of A is a subspace of R4. In other words, J is 4 in this part. But another kind of nice trick about this is if you just memorize one, there's only really one thing that column space A could be. So if you keep in mind that the null space is always this part right here, the number of columns corresponds to the dimension of the null space, R2, then it automatically implies that the number of rows goes with the column space. If you get one down pat, you've got the other. So that's a decent strategy as well. But it's good to know exactly what is the null space, exactly what is the column space, because that helps out with a question like example 7. This one, much like at the very top of the notes, part A in an exam 3 setting and even a final exam setting, it has a way of being pretty tricky. You had to know for this question, it's just A times X. Sometimes people solve this by trying to compute the null space of A and seeing if X is a valid vector in that null space. But that's a totally separate kind of question. It's a pretty large question. Same idea is down below right here. If you're just checking if W's in the column space or W's in the null space, it's good to know just exactly what those two things are. Much like the other exams, when we go to do exam 3, I'm going to have a handout, so a list of theorems, a list of definitions, and those kinds of things. I probably would put down the definitions for both of these because they're so pivotal. But the more you're familiar with them, the more you can memorize what they actually are, the easier they are to use. So let's do both of these problems here. Determine if W is in the column space and if W is in the null space. Let's do the null space first. That one is pretty direct. We don't have to do them in order. We can pick any order we'd like. To check if W is in the null space, we just go here, take A times W. So knowing what the null space is in the first place tells you which subspace it is. And down here, it tells you what to do. So this is going to be A times W. It's a pretty big multiplication, 10, 0, 1, 1. Negative 8, 2, negative 1, 1. Negative 2, 2, 6, 0. Negative 2, negative 2, 0, negative 2. Multiplying W, 2, 2, 0, 2. Okay, so let's take this row dot product with this column. That's going to be 20. Minus 16, so balance of 4. Plus 0, still 4. Minus 4, so we get a 0 on the first entry. The moment we get something like 5, our problem is over. We know it's not in the null space. Now, next one is going to be 0 plus 4 plus 0 minus 4. So 0 again. And don't celebrate early. It's possible you get 0, 0, 0, 1. So we can't make any determinations just yet until we finish the problem. So now it's 2 minus 2 for a balance of 0 plus 0 plus 0. So it's potentially in the null space still. Now it's 2 plus 2 for a balance of 4 plus 0, so still 4, minus 4. So this goes to 0. And we can't celebrate early here. We could lose credit if we stopped just right here in an exam 3 situation, because you have to tell me, what does this mean? Determine if it's in the null space. We have to say, this implies, because we got the 0 vector, W is in null A. This is actually easy to forget on exam, so I need to know that you know what the underlying conclusion is. So don't forget to make those conclusions. Getting the zero vector here is what got us inside the set. Any questions, folks, with the null space part? Okay, the column space part is actually not as convenient. And the author in the reading has a pretty interesting listing of, he calls comparisons and contrasts between null space and column space, how the techniques differ as you try one thing and another. That's some pretty good reading just to kind of put things together. If it comes to finding out what the null space is, that's hard. That's getting parametric vector form. Finding out what the column space is easy. You just span the columns of A. Finding out if a vector W is in the null space of A, that's easy. You just take A times W. But finding out if W is in the column space of A by default is not easy, unless there's something rigged about this problem. So let's put down here just a set of notes that goes along with this. In general, by that I mean as a technique that always works no matter what. If this was a harder problem, we might have had to use this technique. In general, to determine if W is in column A, we must check if AX equals W is consistent. And what does that mean? It means you row reduce the augmented matrix, A augmented with W, and see where the pivots land. If you have a pivot in the rightmost column, it's inconsistent, and W is not in the column space of A. That's a big row reduction problem. So sometimes if you stare at this hard enough, you might see a different way to look into this. Columns of A, if we list it as A1, A2, A3, A4, and then think about what is the column space in the very first place. Column space of A equals span of A1, A2, A3, A4. But span is a tricky definition. Anytime you write down span, you should also have in the back of your mind that the span is also the collection C1A1 plus C2A2 plus C3A3 plus C4A4 such that C1, C2, C3, C4 are parameters, free variables, any real number. So just in R is a short way to say that. So that's a particular linear combination. And if you can find the right linear combination that makes W, you can skip all of the row reduction completely. So let's think about these columns as it relates to W. Let's pause here, do some thinking time. You're looking for the right scalar C1 through C4 to get that combination, make this W. So I'll pause for a moment while we're looking at this and thinking about it. Will anyone see a good set of scalars to try? Yeah, good call. That vector W looks oddly like A4. You just have to multiply that by -1. So if you spot something like that, you've saved a massive amount of time, a humongous amount of row reduction. So good call on that. So let's say it this way. Or let's write maybe W equals 0C1, 0 times A1, 0 is the C1 value rather, plus 0A2 plus 0A3, but then go minus A4. That'd be -1 times this. -2, -2, 0, -2, which is 2202, which makes the statement up front accurate. That is the vector W. That means W can be written as a linear combination of the columns of A. That means it's inside the span. The span of the columns of A is the column space in the very first place. And this one was, again, just rigged so we could really look at that definition and see how it works. At this point, we can just say, therefore, W is in the column space of A. And our job is complete right at that step. If we didn't see this relationship, or maybe it was just a harder problem where W is not nice of a linear combination, maybe it's 1, 1, -5, 4, I would never spot that visually. We would have had to have done the row reduction to make it work out. But anything you can see like that, it's a big help for this kind of problem. And I also want to mention, this is kind of a rare situation. To find the same vector that's in both the column space and the null space already implies your matrix A has to be square. Implies a whole bunch of other weird things in linear algebra. The matrix can't be symmetric any longer. A is not equal to A transpose. It's going to say something about eigenvectors, eigenvalues later on at the same time, but that's going to be our chapter 5 content. So this is a pretty weird setup. This is not something very typical. Any last questions at all, folks, thinking about column space and the null space? Okay, well, there's more content here, but we're at the end of the portions where these would be the typical kind of homework problems, typical kind of exam problems. If you're curious, this section keeps on going. One thing that we didn't talk a lot about in section 4.2 were the linear transformations themselves. So linear transformations are linear if it satisfies these two relationships. This is from chapter 1 as well. But the thing about what we're getting into now is our domain can be any vector space, say the space of continuous functions, or maybe more exotic. And same with the codomain. When we put in this rule, we have some certain problems. There's not guaranteed to be a standard matrix A for the linear transformation. That only works getting a standard matrix if you go from Rn into Rm. So we have kind of a different sort of situation here. So if we're talking about transformations in general, we don't always say null space. We say kernel more often. The kernel of a transformation T is defined just like a null space. It's going to be vectors in the domain V such that the mapping T sends it to the zero vector. But we can't necessarily always fit a matrix multiplication in that equation any longer. So our linear transformations get weirder as the vector spaces get weirder. And kernel is kind of a curious word. It's sometimes used in computer science to say the major core of a program or operating system, the instructions that get loaded in first before anything else happens. Kernel in this sense is just talking about the core, the center. You're mapping to the zero vector of the core domain, of the codomain. So kernel's kind of a strange choice of word there. Range is kind of our equivalent of what we were talking about when it came down to the null space. Or excuse me, the column space rather. So we can't say the span of the columns of the matrix any longer. We write it in this way. The range is going to be the vectors in W such that there's some vector X in V, the domain, and T of X maps to B. So if it were a simpler situation, if we were going from Rn into Rm, what we would almost always do is rewrite T of X as A times X. And in that case, the kernel is the null space, and the range is just the column space. But the problem with that is you can't always do this. Our transformations T, very useful ones, don't always have those domains and codomains. Sometimes the vector spaces are more abstract. And that's what's going on with this problem down below. Kind of a weird problem. It's the differential operator from calculus 1, calculus 2, and so on. So because we have a little bit of time, it's good to kind of revisit what a linear transformation is and how some of these vector spaces work, because vector spaces like CAB They do come up in the later part of the notes. So let's do some portions of these. We won't try to finish them all. Maybe we'll get down to the range, hopefully. Anything we don't finish, I'll finalize the results later on so you can see them if you were curious about the rest of this problem. So here is a non-standard linear transformation, but an extremely useful one. V is going to be the vector space of real valued functions defined on the interval AB with the property that they are differentiable and the derivatives are continuous functions on that closed set AB. So that's the vector space V. It takes a lot of words to say, so there's a great symbol for that vector space V. V equals C1 AB. So this means you can differentiate it one time. That's what the one up here means. And after you differentiate it, your function is still a continuous one. So C1AB. W is the vector space CAB. That's just the space of all continuous functions on the closed set A to B. So D is the transformation that goes from V to W. We could say it more specifically. D is a linear transformation that goes from C1 AB to CAB. It's defined by taking the function f. So f comes from here. That means it's differentiable. Its derivative is continuous on the closed set. And as the name kind of suggests, it just outputs the derivative of that function. F prime is then guaranteed to be a continuous function because that's what C1 was in the first place. The derivative is continuous. So the codomain is CAB, just a continuous function. We can't necessarily guarantee it's going to be continuous again. Continuity can break after you differentiate once. But here's another review from chapter 1. Let's show that this transformation D is in fact a linear one. Any questions with the setup of the problem at the moment? Okay. In a certain sense, this is kind of like thinking about the subspace definition, except that there's just two parts. The very first thing we do is we grab vectors from here. But this time vectors are functions, so we might start by saying, let f and g be in C1 AB. We're going to have to show two parts. So the first part is doing a mapping on the sum of the functions and also doing the mapping on the scalar multiplication of the functions. So we also need a scalar. And let C be in R. So to verify linearity, here's the first part, part A. We have to take the transformation D of the new function f plus g. So this is the scalar multiplication in the space, both CAB and C1AB. But all the transformation D does, it's the differential operator, is this. It differentiates whatever goes into the function. So it turns into f plus g prime. Here's where the problem would get kind of difficult, except we know a lot of stuff from Calculus 1 just by default. One big theorem in Calculus 1 was the derivative of a sum of functions, and they mean this specific sum, the vector addition of those functions, is still differentiable. And it's defined to be f prime plus g prime. So the differential operator is linear in this sense. So feels like kind of cheating, but this is Calculus 1 content that we have already as a prerequisite. So we're free to use what we already know. The moment we get f prime back, that's just going to be right here, the differential operator of the input f, plus the differential operator where we have g prime. That's just plugging g here to get g prime. So we can put g in this spot. And that's the first part of linearity. You can either do the vector addition here, that's in the domain space, or you can do the vector addition here. This is in the codomain space, continuous functions on the closed set AB. So the way you look at this is also important. Notice I never put in the inputs t or x whatsoever. Right where the red dot is, that's one symbol, a brand new function when you take f plus g. And over here, that's vector addition as well when we were looking at those function operations. That whole thing, df plus dg, is one function and it's one symbol to describe that function. So that's kind of wild in a sense, but it verifies linearity holds, at least for this part. We have to show it's going to hold with scalar multiplication as well. So that's our part B next. We take the transformation D, doesn't matter what it is. It could have been transformation like in chapter 1, or a more exotic one like we've dealt with here. Do the scalar multiplication, C times F. This is just one overall symbol for one brand new function, the scaled version of F by C. But we just take this, we plug it into the function and differentiate. So this turns into CF prime. And if you go back to your Calculus 1 textbook, there's a specific theorem that says as well, if you scalar multiply functions, this is differentiable. And the derivative is defined to be C times F prime. This would have been, say, like in section 3.1 of the Calculus 1 text that we typically would take. So once we get here, we just undo the mapping. F prime is df. So this turns into C times df. And that whole output is just the name for a whole new function in the codomain space here. So that's a linear transformation. Because it's a linear transformation, we can describe the kernel. That's just a way to say null space again, but we don't have a standard matrix A for the differentiable operator. That part's the impossibility. It's not going from these kind of spaces. It's going from one infinite-dimensional vector space into another one. These are pretty crazy spaces. But it still has a notion of a null space. We just call it the kernel. The kernel is the collection of all vectors in the domain space, that's the V right here, that get mapped into the zero vector. So we can say kernel, cur for short for kernel, a differential operator D, is this set. Anyone happen to know what the kernel should be just by thinking about properties of this differential operator? Exactly. Every single constant, if you apply the differential operator to it, you get the zero function out. So good call. The kernel to this differential operator is just constant functions. So we can say here, f such that f of x, let's use the input variable t since that's our author's habit in this section. Functions f such that f of t is divided to be c for some c and r, that's the constant. And to make it a constant function, we have to also say, and all t in that closed set, going from A to B. That gets us the kernel altogether. So this is just a fancy way to say all constant functions. What's a little bit trickier is what's the range? Sadly, we're just kind of out of time, but if you're curious about this, I'll fill it out. And the major idea is you have to use the fundamental theorem of calculus part 1. And if you use that theorem, you can show that the range of the differential operator is the entire space, CAB. It's an onto mapping. It's not one-to-one, unfortunately, because the kernel contains a whole bunch of functions, every single constant function, but it is an onto mapping. Well, any last questions at all, folks, thinking about these slightly more bizarre transformations? Okay, kind of weird material. Like I mentioned, this isn't on the homework. I'm not going to ask these kinds of questions on exams. For us, it was just another way to think about null space and column space in a different kind of setting. And most important, think about linearity again, just as kind of a review problem. When we come back next time, we'll be jumping into linear independence in section 4.3. But have a great weekend, folks. Stay safe on Halloween, and we'll be back to it next time. I'll fish out the results of this one if you're curious on just how it goes. How does that fundamental theorem sneak into the problem?